Yeah, thanks. Okay, so I'll just start actually first by just sharing a link to how everyone can ask questions to the panel. So if you click in the chat on Menti, on the link that I just posted, and then you click Open Q&A, you can add a question, and you can also upvote other people's questions that you like. So that's the best way, at least for now, to add questions. And later we might switch to another format. Cool. Animesh, do you want to go ahead?
Sure. I think first let's start with sort of introducing all of the panelists for people who are joining us again. So we have Raquel with us. I would be very sort of hard placed to introduce Raquel to all of the people here. Everybody might already know, but Raquel is currently a co-founder of ABI and is also faculty at University of Toronto. She works on many very interesting problems in computer vision and robotics and autonomous driving. And we are very interested in hearing from her, or we will be interested in hearing from her in the interplay of how vision is needed, or how much vision is needed in interactive and embodied problems. Dave, do you want to introduce other speakers as well?
Sure. So another speaker is Shuran Song, who is an assistant professor at Columbia University. We heard from Shuran earlier her work on deformable object manipulation, but she's also done a lot of really great work integrating 3D vision with robotics in a variety of different ways.
And we also have Sergey Levine with us. Sergey is currently a faculty at the University of Toronto, and Sergey also spends time at Google.
Really?
Sergey is
University of Toronto.
University of Toronto.
Oh, sorry. I was
great. I didn't know that. Welcome, Sergey.
Uh-oh. you gave away the secret, Animesh.
Sorry, I stand corrected. Sergey is currently at University of California, Berkeley. However much I would like him to be at University of Toronto.
I mean, that would be fun. I like you guys a lot.
Sergey works on many topics in reinforcement learning and robot learning. He talked about scalable robot learning earlier today, and I think he would provide very interesting insights from the other end, not from necessarily vision, but also why embodied learning would require vision and perception, and then how much embodiment would be tightly coupled. Dave?
Sure. So the next speaker is Saurabh Gupta, who is an assistant professor at UIUC. Previously, he was at Berkeley. And I guess we heard from Saurabh earlier his work on visual navigation, definitely a pioneer in that area. And I think is Greg here? So we might at some point also have an honorary panelist, Greg Dudek, who is a professor at McGill University.
Greg is here.
I'm here.
And he's done research in a variety of different areas in mobile robotics and autonomous navigation.
Wonderful. So the way we were planning to do this, of course, there are open questions right now, but let's start with a harder question up front, and we can cycle through all of you in some random order that me and Dave will pick. And then sort of we can go from there, and audience are requested to sort of upvote questions that we can follow for subsequent questions. So let's start with a harder upfront question. This is a problem that I have thought about a lot, and also others have. What is a good Turing test for robotics? What would be a cool task that you sort of saw working algorithmically that will tell you, wow, robotics has made like a quantum jump in let's say algorithmic or hardware ability? And let's start with I don't know. I'm just looking at people. Saurabh.
Okay, sure. I could start. By the way, it's very nice to see all of you, and yeah, nothing can replace a real conference, but this is what we have. So I think I don't. I don't think it's one task. I think my worry is if we exactly say one task, then I mean, depending on how narrowly or broadly that is defined, I mean, we run the risk of getting solutions which are highly engineered towards that one task, right? So I think, in my view, I think it is, I mean, I would call it success when we can have robots which can do a variety of tasks. I think that's my starting thoughts.
Okay.
Yeah, maybe others can jump in and I can come back later
Sure.
on. But.
Let me announce the order. So Sergey, Shuran, Raquel, and Greg. Let's go with that order.
Yeah, I was kind of having the same thoughts as Saurabh was, like kind of, sort of a meta thing about robotic learning research for me has always been that it's like the things that I find the most exciting are usually things that a lot of people that are not robotics researchers actually will find really boring. It's like, the cool thing to me is not to show that a robot can do, a superhuman dexterous thing, but to show that it can do something boring as reliably as a person could. And like the boring stuff is kind of the important stuff. But maybe if you, in the spirit of sort of your question, I think what I would say is something like this, that some kind of learning procedure that prepares the robot such that when you put it in some environment, you give it some task in a, well, let's say that in some way that it can understand, and then in 30 minutes it can do it. Let's say 30 minutes, like not instantaneously, 30 minutes. I think that would actually be a really important milestone towards truly general and broadly applicable robotic learning methods. And I don't mean like some crazy task, like something that any person off the street would be able to figure out and do with their own hands, like that. I think that would be a pretty good milestone.
So skill learning in 30 minutes. I think that's like a good sort of goal for people to work on. Good, sure.
Okay, my turn. I think that I kind of feel that we will not come up with a task today, but I think that the high-level spirit of Turing task is that I think the original task is actually pretty general, right? You talk to a robot and you cannot tell it's a robot. I think similar thing applies here. Like if a robot can do some task in a way that is you cannot tell it's a robot is performing it, or like the type of like the process of learning is just like human, or like the way that they execute a task has the gracefulness that is you cannot tell it's a robot. I think that's like share the similar idea of original Turing task. We don't need to actually come up with like an accurate specific task. Yeah, that's my thought.
Cool. Raquel?
Yes, I guess my question will be, why do we want a Turing test for robotics?
That's a good question.
Right, versus can we have a way to measure our progress, as Sergey was saying, towards more general, whether it's learning or not learning algorithms. I guess we are maybe a bit biased on the learning side. While at the same time have demonstrations in the real world of whether you engineer or not, that actually robots can do tasks that are useful for society. And these two things are not necessarily the same. Right, and I think progress on both is fantastic, and hopefully they align, but it's going to take a while to align them.
Wonderful. Craig.
Yeah, great. I get to go after this set of illustrious speakers and fill in the gap that they hypothetically left. I mean, I think the Turing test is a little bit misrepresented, right? Because it's become in popular culture to be some surrogate for AI, but really it's just a question of, can we fool relatively unskilled humans? And it turns out that's a pretty low bar. So maybe it's not really the right test, which I guess is what Raquel alluded to. But I think, Animesh, you're really saying something much broader. That is, what are the really big challenges that would make us feel we've really made it? And I think collaborating with humans in a way where a robot can replicate the behavior of a human in a collaborative environment with other people, I think that's that's an interesting type of metric. I think there are many different kinds. Arguably, the set of things that we can do with robotic systems is actually much larger than what Alan Turing envisioned. So, there's things like autonomous driving, where there's a different class of performance targets than from a collaborative test. I'll mention, by the way, Goodhart's law, which is that idea that, once you define a test like this, then you start working towards that test, and that becomes a artificial surrogate for a real performance. And I think that's been a thing we've seen many times in AI. So in a way, not having a well-defined Turing test may actually be a benefit to the field. So yeah, but I think actually replicating humans in a collaborative test would be a really interesting, I think, benchmark.
Okay, so let's flip the order, and also let's make the question a bit more sort of reachable. What is like one robot application that all of you can feel is going to be transformative at the order of, let's say, 5 to 8 years? So we are not looking at like solving robotics in our lifetimes, but let's say what is one transformative application, and what would be, let's say, what you would call fundamental technical roadblocks or bottlenecks that are standing in our way in solving that problem at a 5 to 7 year horizon. And let's flip the order. Let's start with Greg now.
Well, I think seeing systems that can function in for very long periods of time in a way that they can seek energy or diagnose their own failures or fix themselves or seek assistance. I think that's an interesting kind of target. Like that would, I think, really change the world. So, I'm interested in systems, for example, that might be able to explore parts of the ocean, probably in large teams. But to really substantively solve that task, we need robotic systems that can really operate for a long time at a large scale of space. And I think the kind of things we normally do in our field, we make something a really, really cool demo. It works for a few hours, maybe a few days, maybe even a month if it's a really big win. That's not enough, right? So we have to push much harder, I think. That's one thing.
Cool. Raquel, what do you think?
Self-prepare.
Yes, I think, let's see, I'm gonna give you two answers. I know that you asked for one. I think where we will see more impact maybe is things like warehouses. Okay. Now, if you ask me, although, everybody, my PR team always tells me, never say timelines, I will say self-driving, obviously.
Fair enough. Shuran?
Okay, I was still thinking about it, but okay. So I think first 5 to 7 years is actually really quick, right? In the grand scheme of things of like robotics research, 5 or 7 years probably means that the technology is already there. So I think that's a great question to ask if, for example, you want to do a startup today.
Maybe I want to.
I think it's probably like when you think about what are the technology that are mature enough. I think for structured environment like warehouse, I think anywhere that we can put structure, like even your homes, that we can actually add structures. Like if we just isolate the kitchen area, that's only robot can enter, no human. I think once we can make the environment structured, it's probably something like solvable in reasonable amount of time. So I guess that also answers the second question, is like what's the biggest roadblock, right? It's like, I think even we can make it structured, there is still some unexpected things happen. So the robustness of the system that's dealing with unexpected either objects, scenarios, I think that's the thing that's really, if we think about productionized robotics.
Wonderful. Yeah. Sergey?
So I'll give us an answer that's maybe like goes a little against the spirit of what you asked. That's not about so much about like real world applications in the sense of like something that, a company makes that makes lots of money, but maybe more from a technology standpoint. And my answer is actually kind of similar to Greg's answer, but for a very different reason, I think, or maybe the same reason, I'm not sure, but probably a different one. And it's persistence and autonomy. And the reason that I think persistence and autonomy is so important is actually, I'm kind of coming at this much more from kind of a AI and ML perspective and thinking that, these days, we usually think about, well, how can computer vision help robotics? How can NLP help robotics? How can whatever? I think it's quite realistic to imagine 5 to 7 years from now, we'll be saying the opposite. How can robotics help computer vision, NLP, and all these other applications of ML? Because robots, when they're truly autonomous and persistent, will be much more powerful engines for gathering the sort of experience and data that we need to make ML and AI systems work. And I think we'll, we're already beginning to see some of that in more niche applications. I think we'll see a lot more of that in the span of 5 to 7 years. So I think actually maybe in the long run, kind of a big part of the impact will come from robots enabling better AI in other areas through persistence. And for that, we need to figure out the persistence and the autonomy questions so that basically the cost of those robots doing stuff is lower than the cost of humans doing the data labeling and collection.
That's actually very, very neat insight. Saurabh.
Yeah, so I think I'll also try to dodge the question somehow. But so I think my feeling is I think I kind of agree with Shuran here, which is that I think if you're looking for something in the next 5 to 8 years, it will likely be in somehow if you can scope out a problem, scope out the environment such that there is limited, limited complexity, right? I think that's what will happen in the next could happen in the next 5 to 8 years. Now, I'm not sure if that's going to be transformative. I think what will be transformative is essentially the first application which we can basically which will work in unstructured, real complex environments. I think the application can be very simple, but if something that works in unstructured, cluttered real world environments, I think that will give us the pathway on what we could do. How could we scale that up for other harder tasks and so forth, right? I mean, we realize all the ways in which things break, all of that, right? And once we have once we have a shoe in, then I think we can open the door. I think that's my feeling. But yeah, I don't know if I answered the question.
Exactly. Yeah. Very good way of very many words to dodge a nice question. Over to Dave. Dave, go ahead.
Great, thanks. Cool. So I'll just continue in the next most popular question. But remember, a reminder to the audience to feel free to upvote questions and add questions that you like. So the question is, if you think that we should be focusing more on sim-to-real transfer or more on efficient real-world robot learning. So there's a few different variations of this question that I can add so you can think about different aspects of it. Variations, if you were a government funding agency and someone came to you with wanting to build a much more complex simulator as a big project, would you invest a lot more money in building really great simulators that are diverse, more realistic, things like that? Or do you think, we've kind of hit our limits with how much we can do from even better simulators, and we should just forget investing more time and money in building simulators and sim-to-real transfer, and we should just focus on learning directly from real world data? So we can do the initial order of Saurabh, Sergey, Shuran, Raquel, and Greg. Yeah, Saurabh, do you want to start?
Yeah, so I think if I have to bet money, I'll bet on real world robot learning rather than in simulation and then doing sim to real. And I think partly this is due to my ignorance. I actually don't know how well we can actually simulate physics. I mean, I haven't really played with. I think I have serious concerns about how well we can actually simulate physics. What does it take to build a very good physics simulator for especially interactive tasks, right? So dexterous manipulation and the like. Now, if the effort for building, if we basically go down this path that to solve one problem, we have to build one simulation environment which can allow us to solve that one problem, then we solve that one problem. And then when you go to the new problem, then now again, we have to build a new physics simulator, which is, catered to, modeling things that are required to get that problem right. Then I think if that's the path sim to real ends up going in, then I think we are better off just trying to learn directly with real world data, right? Then you're not quite sharing what one simulation has done for other things. And in some sense, if you look at successes of sim to real transfer, that's exactly what they have been for contact-rich tasks, right? We have the OpenAI result, you have the animal result, but over there, extensive amounts of efforts went into building a very good physics simulator for you to do learning and then doing sim to real transfer. Yeah, so I think if I were to bet money, I would bet on real world robot learning and basically trying to identify, what all do we need to learn? What all do we not need to learn? And then going about it in that fashion. But yeah, that's my 2 cents. I don't know. I see people disagreeing, so let's see what you say.
Great. Well, disagreement is ideal for a panel. So I would encourage everyone to try to disagree with everyone who spoke before them if possible. Sergey, go ahead.
Yeah, so I think that sim to real transfer is a very pragmatic and decent idea for getting things to work. In fact, it's so pragmatic and decent that it's what people have been doing for 50, 60 years. They just haven't been necessarily calling it that. So that the basic recipe in robotic control, where you devise a model of your system and then design some sort of controller against that model. That is the standard way to do robotic control for a very, very long time. And I think that in some ways, you know, the examples of that working well today, they're just reflecting the exact same lesson that, you know, we should have learned decades ago, that yeah, like human learning is very powerful. Humans can devise good models, and then they can, for specific domains, they can use those models to get good results. That said, I think that in many ways, the benefits of such an approach are quite orthogonal to the benefits of actual robotic learning. You know, actual robotic learning to me is a robot figuring out something about the world, not something about the simulator that you build. And I think in the long run, that approach will be better. I think the issue is not that it's hard for us to design simulators. I know lots of people that design simulators for a living. I worked on computer graphics myself. I firmly believe people can design really great simulators if they set their mind to it. I just think that machines learning about the world on their own will ultimately do better. I don't think they'll do better today, probably not tomorrow, but ultimately they will do better because they can simply afford to spend more time on it. You can build lots of robots and have those robots practice things in the world and figure out all the details about how the world works that allow them to get the best proficiency and the best generalization. And eventually they will exceed the limits of what you can figure out to build into your simulator. Basically, the rule of thumb you can use is that in a learning-enabled system, any mechanism that is limited by a person's ability to spend time to engineer it will eventually become the bottleneck for that system. It may not be the bottleneck for that system today, but it will be the bottleneck eventually as the system becomes more autonomous, more persistent, and is able to learn more things on its own. And this is why, for example, for computer vision, we don't use, generally most computer vision systems that are actually deployed are trained on real data. You can do computer vision with simulated images. Our ability to generate simulated images is excellent right now. They just work better when trained on real data. And I think we'll see the same lesson in robotics ultimately. There are, to be clear, I think there are algorithmic things we have to figure out to get there, things like using offline and diverse data sets. But I think eventually we'll get there.
Sure.
Okay. Yeah, so I think this question really reminds me of last year's RSS. I think there's one workshop or debate is actually centered around simulation. And I remember last year I was taking the side that we should have used simulation, something like that. So I can come up with a list of things that why I think simulation is still very important, at least for today, robotics research. Like it's such a big enablers for doing so many different things. But I think another point I was thinking recently is that maybe there is a more blurry line between like simulation and the learning from real world, right? So once you start to think about, like if you want to learn a predictive model, if you want to learn any kind of model from real world data, that can actually be used for your simulation, and it can be maybe used to augment your physics simulator so that your simulator is better without manual engineering. So maybe there is not like a real question about like whether we should go for simulation or real world, and it's just like using real world data to build a better simulator. That's one possible way to think about it.
Cool. Thanks. Raquel?
Yeah, I think the answer depends on the application. So I'm gonna answer from my biased view of the world of robotics being self-driving cars, okay, or self-driving vehicles, I guess not trucks. Let's see. So I think that simulation is extremely important. You cannot do things without simulation. And I think it's not just about sim to real, what about real to sim? Testing is extremely important as well. It's not just about learning new things, but how do I know that my system is able to do something? I cannot just rely on driving billions of miles in the real world to be able to say that this particular software release is actually safe, right? So I think we should look at the counterpart as well. And to me, we need both. What do we even need to pick? If you think about, how do your system learn, is that it should be able to learn from the real world and your simulation, and your simulator should be able to learn from the real world and get better as well, right? So, and you should just improve, continually this thing, right? And if we figure out that, then I think we will be in a much better place.
So maybe I'll just push back for 1 second to create some more discussion. So I guess part of the reason why I was framing it as, let's suppose you work for the NSF, you have 2 grants. One that says invest, $2 million in building a better simulator. There says invest $2 million in collecting real robot data and learning from it. Like, which one are you going to invest in?
So David, you didn't let me go yet, and I'll answer
Yes,
that in the
definitely.
context. I think that it's, in my opinion, it's clear you should invest in a system that can learn from bad simulation, because that's what people do, right? I know people who run forestry companies, and they take human beings who don't really understand the domain very well, and they give them astonishingly simplistic simulators. I'm trying to find a word that's not too impolite to I'm translating those companies. And people learn from them very effectively. So I think, to take Sergey's point partly, the better your system can learn, the less it depends on a good simulator. But having no simulator would, I think, be foolhardy. I mean, in some sense, mathematical analysis is the most primitive, well, in some sense, primitive form of simulation, and we would never think of doing without that. But I think Raquel makes a great point that if the simulator itself can learn, of course, the reality gap can be closed by the simulator as well. And so, it's very hard to say one or the other, because in some sense they end up becoming a very similar problem, right? If your underlying learning machinery allows the simulator to adapt in the same way that your robotic system adapts, then you may be able to close that gap with a single investment. Although I'd put it on the robot side, mostly because I'm a robot guy.
Thanks. Does anyone want to add anything to this now that people have heard other people's answers?
I think NSF should add more money for fundamental research so that you can have both grants.
Great. Okay, I'll hand it back to Animesh.
Absolutely. So I think one of the next questions also refers to a point that Sergey mentioned earlier about persistence in autonomy. Sergey mentioned this and it came up as well. What do you think, how can robotics research actually contribute to our understanding of intelligent behavior and intelligence in comparison to what other fields cannot, like what, let's say, people in neuroscience, cognitive science, NLP, computer vision are studying? What is the special thing that we can do that others may not be able to do? And let's flip the order again, or maybe let's randomize the order. Let's start with Sergey this time.
Okay, I mean, I guess since I don't have very much time to think about this one, I'll say something that's a little bit similar to my previous answer. But I guess the perspective I have on this is that the robotics problem is essentially the AI problem with sort of many of the training wheels removed. Like if we study RL agents for playing video games, we have some training wheels in there where like there's certain aspects of the problem that are abstracted away for us. If we study AI problems in the context of like conversational agents, we have some issues that are taken out of the picture. In robotics, you really have to deal with the whole thing, which means that you can still take some shortcuts, but the shortcuts are much more limited. And I think that serves as a really powerful lens to focus us on the problems that might otherwise be missed in an overly decomposed approach. What are the important parts of the AI problem that the computer vision community is missing? What are the important parts of the AI problem that the NLP community is missing? If you work on robotics, chances are you'll get a significant amount of clarity on which bits people aren't paying enough attention to and which bits are really like going to be major roadblocks. I think Moravec's paradox has, in my opinion, been an enormously influential idea in shaping our understanding of AI, and that's an idea that really comes from confronting the full brunt of the robotics problem. So I think all the technological stuff aside, just for us as scientists, I think the focusing effect of working on robotics, of how it helped us understand just how far we are from getting the AI problem right, I think that's like one of the most important things.
Wonderful. So let's go with Raquel, Greg, Saurabh, and Shuran. So Raquel.
Great. Let's see. I think maybe two things. One is a bit related to what Sergey was saying, which to me, if you look at, let's say I came from computer vision, okay, / computer graphics. So if you look at these communities, oftentimes it's about deciding on a well-scoped problem that you kind of reduce, and then you try to solve this one problem, right? But by solving small scope problems, you can't really solve an entire system problem. You will never come up with the right solution. Right? So to me, robotics really elevates the thinking to now I have to have this holistic view of the entire thing. How do I go around researching and solving such a difficult problem? And then you come up with solutions that are very, very different. You make compromises everywhere, but you have better end results. And that's very, very different in flavor. And so I think that's one big difference. And the second big difference is, I don't know you guys, but I like to do everything in my life for a purpose. I'm very, very driven. I need to have a reason why. Maybe this is why I love sports with a ball. And I think robotics is like this, right? It's like you're doing, maybe you're looking at perception or something, but because you want to solve an end task. And I think it's fascinating to do it that way. Versus open problem, maybe there's a benchmark, but who cares about the benchmark? And then maybe it's about having a good number, like who cares? Right?
Thank you. That's actually a very good point. I like sports with the ball analogy. Eye on the ball. Greg.
Yeah, I mean, it's hard to disagree on this because I think Sergey and Raquel really kind of hit the nail on the head. But I think the holistic nature of robotics avoids reductionist solutions that don't scale. And I grew up in a world where people still remember Bloch's world computer vision, which was essentially a decade of researchers working on a problem that turned out not to actually fit in any context, not to be useful by and large, right? And so I think robotics precludes that kind of thing because it's very hard to invent a robotics problem that is accepted by the community, that is a little piece of some robot and doesn't fit into any actual robot. I mean, that doesn't work. And so I think that's wonderful. I think it's also worth being a little bit wary of, worth being wary of the fact that the kind of solutions to the intelligence problem that we develop may not be the same kinds that people have. And so there's a lot of people in psychology are like, artificial intelligence, we now understand the human brain. And that's tremendously seductive. And I think it's actually potentially dangerous and misleading in the sense that the more complicated and sophisticated the solutions get, the less likelihood there is that they're the same solutions, the same underlying mechanics. Obviously, so.
Okay, so to add a bit of spice to discussion, and as a counterpoint to Greg's, so that Shuran and Saurabh have more interesting talking points, how does one even figure out what problem to work on? Perhaps like it's a good idea in principle to work on the big picture problem, but what if the components don't exist, right? A lot of robotics has only recently started working when vision actually started working as well. 10 years ago, the approach to robotics was still the same. It's just things were not working. Not even the individual components were working. So the impact of your work was limited. How do we go around that? So we have Saurabh and Shuran.
Yeah, so I think, I guess one way to phrase it is that, so robotics is, in some sense, is going to subsume some other problems, right? I mean, so that has already been said. And I think the implication in the subfields ends up being the loss function, right? So if you think of computer vision problems outside of robotics, you will end up with, what problems, I mean, like, for example, like all the work on internet data, right? I mean, it's driven by a very different loss function, which is, what can you do with it on the internet, right? And you would like to search that, you would like to find objects and all of that. And that led to all of this work in recognition, for example. Now, if you now also start thinking about data from robots and so forth, that might motivate different problems, right? And I think my favorite example is videos, right? So if you look at data sets in computer vision, which deal with videos, they're basically classification data sets, right? So sports, 8 million, whatever you have, right? They're generally action classification, action detection, these kind of problems. Whereas there is just so much more to learn from videos, right? I mean, again, just for some context, we have a lot of these recognition problems on videos, but then the trouble is there's just so much bias in setting up a good recognition problem on videos, right? They will always see that models will never pick up on people swimming, they will just pick on the water that is there in the sea. Now, if you cast this problem instead from this point of view of how can you learn intelligent behavior by watching videos, by watching someone else's video, by watching, right? Then suddenly new problems emerge in the field, which you may not have thought of without this contextual setting of, data in context of robots and so forth. So I think that's kind of my view, which is essentially, the robotics problem gives gradients to all of these other fields, and then they can, optimize the right thing.
Cool. That's actually a very neat insight. Sure.
Okay, yeah, so I think I will first answer your original question, like what is the difference? I think like robotics compared to our other fields. I think there's one very obvious one that I'm surprised that people didn't mention is that in robotics, you actually can change your data distribution like by using active actions, right? And I think this capability of actively changing the world is a superpower that other domains don't have. And because of that, actually, if you think about like computer vision or NLP in a robotic setting, the task maybe can be drastically simplified just by like using this kind of active interaction, like object recognition. You can simplify it by using some interaction, or like video understanding. You can control your camera positions or control the way that the data is gathered in order to like redefine the computer vision problem. So I would say that is like the biggest difference. And I think that's also like, if you think computer vision or NLP in this kind of setup, a lot of problem will be redefined. And maybe I'll get back to Sarah's point, is like the loss function is actually quite fundamentally different. Yeah.
If I can just comment, I think that's a really interesting position. Sorry, as in I can't comment, or I'll comment anyhow. You'll have to try harder to stop me. I think it's a really interesting position because I think a lot of the time I think of robotics as being the hardest area to work in because of this confluence of many constraints. There's liveness, there's real time, there's variability, there's underlying change. And so the idea that you can exploit that to make the problem easier in some sense, I mean, people in active vision have made those kinds of claims at times. I think that's a very surprising claim. I love it. I don't know if I believe it, but I think it's very refreshing.
Yeah, we have a lot of examples of like how to make a perception problem easier with interaction, right? You pick up the object to recognize instead of like recognize object in cluster. And I also remember, I think the idea, I got it originally from like David's job talk in Princeton back then. I think one of the terms that really caught me is the robotic scientist. It's like the robot can perform controlled experiment by themselves, which very hard to get with passive computer vision tasks. And I think that's really like changed my view of thinking about computer vision tasks and maybe even get into robotics.
Wonderful. Thank you. David, over to you.
Sure, thanks. So I'm actually going to ask a question that wasn't yet submitted, but that I became very curious about when hearing the different talks. So I noticed that 3 of the speakers, namely Sergey, Saurabh, and Abhinav, all talked about visual navigation tasks, and they all talked about using a semi-parametric topological, some kind of topological memory or map. And in my mind, this is sort of a little bit of a change from some of the past work in machine learning, where all of the learning is compressed into at least typically in most modern methods, all the learning is compressed into a fixed number of parameters, say parameters of a neural network, for example. I'm curious if people think that using an explicit memory or non-parametric methods in general is going to become increasingly popular in robot learning, or that's more restricted to certain subfields. So as an example, for autonomous driving, should we build methods that have a memory of vehicle interactions and all the ways that we've seen vehicles and say pedestrians or other objects interact with each other, or should we as an explicit memory or for other applications as well, or should we compress everything we know into a fix of say neural network or some other method parameters? So I'll go in the order Raquel, Shuran, Sergey, Saurabh, and Greg.
I thought you were going to ask the 3 that have the common common talk. Let's see. I believe in hybrids of these things, meaning, for certain things, non-parametric or memory-based things make a lot of sense. Maps are one example. These maps don't necessarily need to be like what humans think as maps. They can be, latent representations that are useful for robots, but not necessarily for people. At the same time, that doesn't mean that you're going to memorize everything you have observed in the world. That's not how these map representations are. You still need to condense them somehow in a way that you can use them. But things that you were saying, okay, do I need to memorize maybe all the behaviors that I have seen? So retrieval-based methods actually work really well if you have the right representation for accessing. And I like these things more and more these days. So I think there is a lot to be done there. While at the same time, being hybrid, meaning with learning a lot of the underlying cost functions and things on those retrieve-based things. So I think we will see more and more of this kind of approach, and navigation makes a lot of sense, right? In the past, it's all about you predefine a map, you load it, and then you go with it. Right here, you can build it as you go, and it can be more sophisticated. And I'm saying this without seeing your talks, guys. So sorry if you talk about something totally different. But I think, I will put my bet on a hybrid of these things.
Cool. Shuran.
Yeah, I don't know whether I fully understand the question, but I will just try my best. I think the question is about like the state, kind of like the representation of knowledge, state representation. I think there.
I can try to rephrase it if it's helpful. So I guess a simple way of saying is, do you think that we will have more methods that have explicit memories, or that memory isn't that important? Like explicit bank of keeping track of past interactions, and as you see more data, you keep that around and continue to access it, or we don't need to have the explicit memory?
I see. So I think we'll probably all agree with like memory is important. It's just like the representation of memory, whether it is explicit as image frames or it's like a learned latent representation, right? And I think that really depends on, I think the practical, it's more on like the practical use case or like the constraints. My feeling that is probably, it will be learned latent representations instead of explicit knowledge, unless we have very strong part about, like, for example, map is useful to store. But even like for humans, I think the majority of the knowledge that we store is basically in a latent representation instead of very explicit memory bank. So yeah, I don't know too much, so I will probably let other people answer that question.
Okay, Saurabh?
Yeah, so I think, maybe let me just recap a little bit. So I think, so in at least in our case, I think we were basically, there was a parametric and a non-parametric version, right? So the parametric version is you're looking at images and you're making semantic predictions, and those are basically learned using a parametric function. Now, the non-parametric part was happening at test time. When you're going around in the environment, you are kind of explicitly storing what you have seen and then using it, right? Now, I think there are two ways to think about what's happening, right? So first is speed of learning, right? If you have to train neural network weights, you will need many updates that you have to do before you can start remembering things, right? So that's why at test time, it makes sense to use something which is non-parametric, because then it makes it very easy to store it, right? Now, the second aspect is, what does the representation, what queries or what properties does the representation have, right? So when we're doing neural network training, which is like estimating parametric functions to explain ImageNet classes, then in some sense within the network you are actually learning lots of associations which you didn't quite think of before, right? So you're kind of extracting out shared things and so forth. There is some sort of, right? So you're doing that. Whereas in the other case, when you have explicit representations, you're not quite, you are in some sense limited by the explicit nature of what you have decided, right? So in our case, for example, the graph is very explicit. So now you can't quite do something that the graph doesn't allow you to do. You can do what the graph allows you to do, which is path planning, very well, but you can't quite do beyond that. You can't quite do something which is beyond that. Whereas like this parametric kind of things, there is some generalization and all of those things which happen. And this comes at a cost, right? So the explicit parametric, the explicit non-parametric stuff is fast, but it only does what you want it to do. The non-parametric stuff, the parametric stuff is slow to train in some sense, but can generalize better and all of that. So I think that's kind of my take on this.
Cool. So I guess before the last two, I'll maybe try rephrasing a question. So previously, I think in the history of ML, non-parametric methods were popular with kernel-based methods and non-parametric Bayesian approaches. And recently, that's gone away, and we've gone to parametric methods, although with a very large number of parameters with neural networks. But are we going to see a resurgence in non-parametric approaches, or that's really just restricted to navigation? Yeah, Sergey, do you have thoughts?
Well, I think that at the risk of offending anyone, I think the literal answer to your question is no, because non-parametric methods don't scale to large data sets. And if you want things to work in the real world, they need to scale to large data sets. But in regard to graphs and things like that, so I mean, I think Saurabh's explanation was actually very good in this regard, and I mostly agree with what he said. Like, it used to be that people thought that we need explicit knowledge representation. I guess used to be, this is more like, several decades kind of timeline, that we need explicit knowledge representation because it's hard for learning methods that use small models to encapsulate lots of knowledge. It turns out that neural nets are actually extremely good at long-term memory. We don't need explicit knowledge representation for long-term memory. Neural nets can do that. What they're apparently not so great at is short-term memory. So there, you have RNNs, you have sequence models, and so on, but that's something that has taken a lot longer to get right. And arguably, sequence models have only really started working quite well over the last 3, maybe 4 years. So in a sense, at least in the work that I presented, and it sounds like this kind of, based on Saurabh's answer, that his perspective is kind of similar to this, that the non-parametric component is really playing the role of short-term memory. You can almost think of it as a kind of meta-learning procedure where the neural net is the one that's really learning things, and then it's just learning how to utilize a short-term memory represented in a non-parametric way. Now, the other part of the question was, well, the graph part, does it need to be a graph? I don't think so. I think we could, at least for the thing that I presented, we could have probably figured out how to do it with attention. We had the graph thing already and it was already working. So, we wanted to focus more on large data sets and getting a robot to drive around. But I think, if we were doing this again, maybe we could try to do it with some self-attention scheme, and that would probably work for the same reason.
Cool. Great answer. Greg, do you want to add anything?
So I'll give you my answer in 3 parts. I think one is, I think the question is arguably not well posed in the sense that the things that once you take a problem and reduce it to practice, you have a finite domain, you're implementing it in some system, then the difference between these methods may be not readily observable. And so I think non-parametrics look like they're kind of, there doesn't seem to be a good reason for people to go back to them, but in practice, it may not matter so much in restricted domains. I started, Sergey talked about way back in time, decades ago. I started my career with, my first paper in 1990 was on graph-based learning graphs. And so, I have a certain affinity for those kinds of methods. And so, I don't think that's going to come back as a mainstream, but there is a fashion trend in our field. I think that things that people don't use anymore become attractive because we all want to find something that nobody else is doing. And so even though the parametrics may be the logical, scientifically appropriate methodology for today, and that's certainly what we all believe, that's what I believe, I think there are sort of other social factors that may drive us to poke into other domains. And I think the last aspect is the issue of interacting with humans. If we want to have systems that have either better cognitive penetrability or we want to pick them apart and communicate with them for some other reason, there may be other driving functions as well that motivate methods that are different from what the big fashions are now.
Cool, thanks. Animesh, do you want to ask the last question?
Sure. So I think one thing that I have always sort of found interesting is often a lot of discussions in robotics particularly is a bit more, let's say, lopsided towards computer science. But at the same time, we do agree, or at least I would hope we do, is robotics is a very broad set of disciplines, computer science, mechanical engineering, EE, and so on and so forth. And all of you, just yourselves on the panel, work on very different subfields of robotics, from indoor navigation, manipulation, outdoor navigation, marine robotics. So would you say in your own sort of area of interest or domain of interest, have we converged on the robot hardware? As in, do you think a lot of your problems can be solved just with better hardware and you don't need to work on algorithms really? Or is it more like we have converged on the hardware? Peter gave a very recent talk at CVPR where he started with this video. We want to sort of solve PR2. PR2 could be teleoperated, hence the hardware exists. We need to work on robots. Or there's a similar debate in autonomous driving where people are arguing, do we need sort of RGBD or can we just do away with the depth part and only operate with the RGB sensors? So I'm just curious, what are your thoughts in your domain or broadly that how much hardware innovation will play a role in your sort of subdomain? Maybe let's start with, I don't know, Shuran.
Okay, yeah, so I see that video and I think that make a good arguments, like feels like everything that we want to do is like the hardware is already there. I would say that definitely hardware is good enough for something. I feel for a lot of tasks that we are interested in. I think we should be very thankful, like it's because of all those developments in mechanical engineering and control get us today that we can actually study those interesting problems with the existing hardware. But I think if you look at on like a more higher level, it's really like an iterative process, right? So we kind of develop certain hardware to a certain level, and then that's also the reason why a lot of software are designed that way. And then we come back to see like whether we can come up with better hardware design. But I think we are also in this very interesting like time, or we have new opportunities to really think about this hardware and software co-design or co-evolution. I think back then it's more on like the experimental stage because making hardware, like manufacturing hardware, is expensive. Like we never think that it can be an inner loop to optimize. But because of all those like advancements in manufacturing, 3D printing, I think maybe we have a lot of new opportunities. Like really also think about improving hardware as part of the policy, like hardware as policy. Yeah. So I guess my answer to that question is, I think the hardware is good enough to do something, but it's definitely not like we don't need to improve it at all. And I think the future is really to think about this software and hardware co-design, if possible. Yeah.
What do you think, Sergey?
I think that figuring out the right robotic learning algorithms will make it possible for us to design the right robotic hardware. Because the kind of robots that people build are, they're necessarily informed by what you can control. And the more your capabilities to control all sorts of weird stuff improves, the more freedom you actually have to design robotic hardware that focuses on capabilities rather than ease of control. Now, that's maybe like a little bit of a learning chauvinist kind of perspective. So I will gently temper this perspective with an anecdote about a setting where hardware was definitely a limiting factor in some of my work. So my student, Animesh Gupta, and I, we recently did some work on dexterous manipulation. The first device that we bought was a robotic hand manufactured, a commercially available hand for research by a company that I won't name. And when we ran our reinforcement learning experiments, it caught on fire. And we had to get the fire extinguisher and things like that. And eventually, with the generous help of Vikash Kumar, who's now at FAIR, we actually redesigned a robotic hand from scratch with the express purpose of making it suitable for learning. Now, the main criteria to make it suitable for learning was just that it wouldn't break so easily and it wouldn't catch on fire. So the kind of considerations that you have, they're still going to be informed by your control strategy in one way or another. It's just that it may be that it's not about ease of control, but more about things like robustness. Human hands are actually very robust, more robust than robot hands in many cases. So I think of course that relationship is not going to go away, and that you do have to inform the hardware by what you're going to do with it. But I do think that good learning algorithms will give us a lot more freedom to be creative and to experiment with the kind of hardware that we use.
That's very interesting. Okay, so to add sort of spice here, we are in the last few minutes, I would add like the hardware chauvinist view. I would argue every 5 to 10 years, every like a piece of hardware or a system, like a working system comes along that changes the way a lot of people do research. And I'll give you 3 examples. One before my PhD started, that according to me was Kinect. Before Kinect, robotics was very different, and Kinect came around 2008 and 9, and sort of like it just changed the way people were doing manipulation. I can say that. When I started doing PhD, robotics, at least robot arms, were 300,000 plus. PR2 was one of the examples, and there were very few of them. By the time I finished up, they were 20,000. We were using X arms and sort of Francas. A lot of people in the groups have access to them, and now people have gone to X arms which are like sub 10,000. I would argue a lot of machine learning people or even vision people, I'm being incendiary here, would not be working on robotics had that not been the case. The fact that you can buy it, it's easy and works out of the box is the reason why a lot of people who were not previously roboticists are now roboticists today. And the same can also be said by legged robotics. It used to be a space of robotics, which was very hard for people to enter because the amount of control theoretic or sort of like legacy knowledge was too much. So there used to be Sangbei Kim, the cheetah person, and there would be like 5 other people in other places, and that's it. But today, you can buy an A1 for 10K, and everybody can try sort of legged robotics. I can say, just sort of defacing myself, that I have started doing this. So maybe that is like the hardware chauvinist view, where like without this, a lot of people who are doing and calling ML would not have the hardware to do this. So maybe next goes like Raquel, then Greg and Saurabh.
Yeah. So let's see, and I really like your 3 points, I guess there. I think that I agree with you that hardware and software go hand in hand, and there is some breakthroughs that make your life much easier. And I think, again, putting my self-driving view of the world. So we have the hardware, right? Meaning that, as a human, you drive with 2 eyes. You can actually, remove one of them, or, maybe put something in front instead of removing, and you can still drive, right? That doesn't mean that that's how we should do, self-driving vehicles, by just having the minimal set or the worst case of hardware that we know that this can solve the problem. For me, as a, more of a software person, right? Hardware is the way to cheat. And I'm very, very happy to take the latest, greatest that enable us to focus on the next big problem and not necessarily the one that we have right now. So definitely, when you're trying to solve a real world problem, not necessarily just in the lab, hardware is an absolute must that you really need to consider.
Cool. Thank you. Greg?
Yeah, so I mean, this is like getting a bunch of salad company owners to debate whether hamburgers are going to be the future. So I was the chair of the computer science department for almost 10 years. Of course, I really honestly believe that computer science is the dominant field in every university. And the only thing that should be more dominant is robotics. That said, I think the synergy of hardware and software is incredibly important. I mean, since I've been running a lab for Samsung, I've doubled down on that because, I learned this whole new world of things. And I think there's a lot to be done on the hardware side. And I think the really beautiful thing about robotics that we should try to hold on to is that merging of the hardware side and the software side, classical control, modern control, RL, all these things together. That's actually what I think makes robotics such a wonderful academic discipline, better than computer science in some sense. I mean, not that it's a competition, but it's that synergy is awesome. But for sure, I think it would be presumptuous to say, hey, listen, hardware is done because it's already been stable for 3 years. I mean, that's just crazy, right? Like hardware is moving pretty fast. And I think the bigger problems are turning into big sets of smaller problems. And so maybe that's less astounding, but there's still lots to do. However, I'm still in computer science.
What do you think, Saurabh?
Yeah, so I think so Peter's video of this PR2 being teleoperated is a very good one, except it only makes the point that at test time systems can operate. I mean, we have hardware which at test time can do what we wanted to do, right? Now, it doesn't make any claim about how the system was trained, right? And in fact, humans were trained with a lot of other sensory information that was available to you when you were a small baby and all of that, right? So I think, I mean, it's a bold claim, but I think if you're thinking of learning systems and if you're thinking of, self-supervised kind of learning systems, I think hardware is quite a bit of a limiting factor, and we'll need a lot more effort before we can actually think of systems which can actually just learn just by interacting with the world. I think that is a vision which is too far in the future. That's all I would say.
That's very nice. I think I couldn't have sent it better, both Greg and while I agree with Sergey in the sense of like the learning chauvinism, it's sometimes like good to think from the other perspective, walk a mile in other people's shoes. In any case, I think this has been a wonderful debate and a panel discussion. We are 5 minutes over. Thank you everyone for sticking around. Some of you, this is fairly late in the day. I personally had a lot of fun. I hope you did as well. There were a lot of takeaways, but I think for me, interesting takeaways, Sergey said it earlier, we need to work on sort of problems which are trainable very broadly, quickly. Raquel added that we really need to think about hardware and software together, but hardware is a good way to cheat for now. And Shuran added interesting thoughts on simulation, that we can actually be sort of thinking about simulation in senses where robot is active, so we don't have to solve the same hard problems that vision people are solving, probably make it easier. I think Greg also gave a very sort of mellowing point that while we would all want CS to be the most important department, we need to realize that robotics is the most important department. With that, I think we can bring this to a close. Thank you, everyone. Thank you to all of you for such nice participants. And Dave, do you want to add anything?
And thank you to the organizers.
Thank you.
Thanks to the organizers.
Yeah, thanks everyone.
Thank you. And have a nice day, rest of the RSS, and hopefully we'll see you around.
It's a real pleasure to see you all. Thanks.